Okay, moments and centers of mass. Our main objective here is to find the point P on which a thin plate of any given shape balances horizontally, as you can see here in figure 8. This point here is called the center of mass, or a center of gravity of the plate. So we first consider the simpler situation. It's illustrated in figure 9, where you have two masses, M1 and M2, that are attached to a rod of negligible mass on opposite sides of a fulcrum and at distances D1 and D2 from the fulcrum. So the rod will balance if we have the mass of 1 times the distance 1, which is equal to the mass of 2 times distance 2. This is an experimental fact discovered by Archimedes and called the law of the lever. Think of a lighter person balancing a heavier one on a seesaw by sitting farther away from the center. Now suppose that the rod lies along the x-axis with M1 at x1 and M2 at x2, and the center of the mass at x bar. If we compare figures 9 and 10, we see that D1 is then equal to x bar minus x subscript 1, and D2 is equal to x subscript 2 minus x bar. And so the equation in equation 6, we're going to take mass 1 and multiply the distance 1, which is equal to the mass of 2 multiplied by the distance 2. And then if we distribute and then isolate x bar on one side and everything else on the other side, and then solve for x bar by factoring it out, then we get x bar, which is equal to mass 1 x1 plus mass 2 x2 over the mass 1 plus mass 2. So here you can see the figure 10 giving our deriving the formula to get x bar. Now in general, we have a system of n particles with masses m1, m2, and m subscript n located at points x subscript 1 all the way to x subscript n on the x-axis. And it can be shown similarly that the center of mass of the system is located at the following. So x bar is equal to the summation of I is equal to 1 to n of m subscript I x subscript I divided by the summation of I is equal to 1 to n m subscript I, which then gives us the following. So now, where m is equal to the summation of m subscript I is the total mass of the system and the sum of the individual moments. So here we would have the total m, which is equal to I subscript I is equal to 1 to n. The summation of that is taking the mass times x, which is called the moment of the system about the origin. So then equation 8 could be rewritten as m times x bar, which is equal to m, which says that if the total mass were considered as being concentrated at the center of mass, x bar, then its moment would be the same as the moment of the system. So now we consider a system of n particles with masses m1 all the way to m subscript n, located at the points x1, y1 all the way to xn, yn in the xy plane as shown in this figure. So by analogy, with one-dimensional case, we define the moment of the system about the y-axis to be the following. M subscript y, going from the summation of I is equal to 1 to n of m subscript I, x subscript I. And the moment of the system about the x-axis as m subscript x then becomes I equal to 1 to n m subscript I, y subscript I. Then m subscript y measures the tendency of the system to rotate about the y-axis, and then m subscript x measures the tendency to rotate about the x-axis. As in a one-dimensional case, the coordinates x bar, y bar of the center of the mass are given in terms of the moments by the formulas. So x bar is equal to m subscript y over m, y bar is equal to m subscript x over m, where m is equal to the summation of m subscript I, which is the total mass. Now, since if we multiplied both sides by m, mx bar is equal to my, and my bar is equal to mx, the center of mass x bar y bar is the point where a single particle of mass m would have the same moments as the system.